This is my physics lab 2, where we studied the motion of a falling object. So for the introduction and background info, the main physics concept that we studied in this lab was Newton's second law. This law states that the change in momentum equals the change, or over the change in time equals the net force. So in lab 1, we had something moving with a constant velocity, so the net force was 0. In lab 2, we observed an object falling. In my case, I observed a plastic bag, and so the net force is not 0. We actually have an acceleration downward due to gravity. And this problem is crucial to studying forces in general, because this is the most basic example of forces, and we have to understand how to do this example before we get into more complicated examples of forces. So this object, since it's falling downward, it should be accelerating at a rate of 9.8 meters per second squared. And we built computational models, one with only the force of gravity and one with the force of drag upward as well. And we can observe how the second model more accurately predicts the motion of the plastic bag, since air resistance is actually quite high for the plastic bag. So here's a demonstration of Newton's second law. We can see how the elephant and the small object on the right can accelerate downward at the same exact rate with no air resistance, since their proportionality of force to mass ends up being the same. So if we go and look at my tracker model, here I have it right here. We can see the plastic bag falling, and tracker actually shows this data over here of y position versus time. We can see that this is not linear because there is a net force acting on the plastic bag, and it's actually exponential, so it's accelerating downwards. And then we have all of our data for t, x position, and most importantly, y position here on the bottom. So if we summarize it, we built a model through tracker, and we used point mass and extracted data for the position versus time, most importantly, the y component, to then compare it to our computational models. The first computational model I built through Glowscript was only gravity, so there was only a downward force pointing on the plastic bag, and this model definitely overpredicted the position of the plastic bag because air resistance was not taken into account, and the plastic bag has quite a lot of air resistance. So we can see this computational model right here. This is how I wrote the program. It is exactly the same as our lab 1, except the only thing that's different is here we have the drag force is equal to 0, and then the time is 0.635. And then our F net changed. We actually have the force of gravity in the y component. Everything else is essentially the same. We have some arrows printed, and when we run the program, it looks something like this. We see the position versus time. It looks very similar to the observed graph. And the velocity is constant, pointing down because we have a constant acceleration downward. Now, if we look and compare this to the second model, here air resistance was taken into account. So in our F net, I actually included a drag force pointing up. And to find this value, I used the square of the speed of the plastic bag, which is the absolute value of velocity. And I found a proportionality constant by guessing and trying to reach the same final position as the observation and tracker. And we can see how this model is a much better representation of what's truly going on with the paper bag. So if we look at our second model in just a second, we can see that I found my proportionality constant right here, 0.012, just by guessing and checking. And then we have our F net, we have our FD, which is our normal force, or not our normal force, our drag force pointing upward, air resistance essentially. And we see that I squared the y velocity and then multiplied it by the proportionality constant. And our F net is just these two forces added together. And then everything else is the same, including the arrows. When we run this program, we can see what this looks like. We have an arrow pointing up, slightly different position graph, and a slightly different velocity graph. And the final position on this position versus time graph should be the same as the observed. So when we compare these two, we can see that model 2 is a much better and accurate representation of what's truly going on with the paper bag versus the model 1, which overestimates the y position by quite a lot because there's no air resistance taken into account. Again, here is a summary of everything I've said. The first model overpredicts that position, but you can see that in the beginning, all three graphs look quite the same because drag hasn't come into play yet. Now, what does this all mean? So terminal velocity happens when the force of drag pointing up exactly balances the force of gravity pointing down. This means that the net force becomes 0. But if we look at my models, both the first one and the second one, we can see that in model 1, the velocity versus time graph is constantly pointing downwards, meaning that it never levels out and is never straight. And same for this one over here for model 2. It's never a straight line, horizontal meaning, and thus neither one of my models ever reaches a terminal velocity. Now the what if of this lab. If the object was initially thrown downward, the terminal velocity would actually be the same as when my object started from rest. In my models, the velocity doesn't even start exactly from 0, it starts around negative 0.5, but either way they would reach the same terminal velocity. So if we look at one of my models, if we started with the initial velocity, it would just start lower down, maybe here or here somewhere, and it would be the same straight line down, but it would reach the same terminal velocity as if it started from 0. So here is a summary of everything I've said, but I believe the magnitude of the terminal force would be the same, or velocity would be exactly the same as if it started from rest. So this was my physics lab 2. Thank you.